So today I'm going to tell you about a new data management system to store data generated by smart homes. So the world today is full of sensors and smart devices, ranging from personal devices like fitness trackers to a bunch of sensors and smart devices in our homes, for example, occupancy sensors, thermostats, energy sensors, security cameras, to name a few. According to a study conducted by Cisco in 2008, the number of sensors exceeded the number of people in this world. And in 2020, it is projected that there will be 50 billion sensors. A domain for which these sensors and smart devices have become inexpensive and readily available is the home. And this commoditization has also given rise to a number of platforms like HomeOS and Mikasa Verde that manage these sensors and smart devices and help applications program them and interact with them. But now, there is a new class of applications that share data across homes. For example, Energy Data Analytics compares energy usage across homes. Digital Neighborhood Watch shares security camera data among neighbors. These applications cannot be easily developed today because they need something beyond the local file system abstraction presented by HomeOS and Mikasa Verde. So the question we are asking is, what are the data management requirements of these applications? And how can we design a system to address them? So to answer this question, we had to first understand the requirements of these applications. So applications for smart homes generate data that is naturally time series, and they look at data from specific time windows. Consider the example of PreHeat. So PreHeat uses occupancy levels to efficiently heat homes. So PreHeat talks to the occupancy sensors and asks it to record the occupancy level of the home for every 15-minute period during a day. So it divides a day into 96 slots and records an occupancy level for each of these slots. This data is inherently time series and has an append-only nature. At the beginning of an upcoming slot, PreHeat predicts what the occupancy is going to be and accordingly adjusts the thermostat. And the particular algorithm PreHeat uses looks at the occupancy level of the past slots of that day and the corresponding slots of previous days. So it requires looking at data from multiple time windows. So it requires support for time series data. Applications for smart homes also access data from multiple homes. Consider the example of energy data analytics. So an energy sensor runs in a home and it records energy consumption data along with the ambient temperature. So each record here consists of the time of the reading, the energy consumed during the last time period, and the ambient temperature. Now the utility company analyzes this data. Specifically, it plots the average hourly energy consumption as a function of the ambient temperature, and it does so for multiple homes, comparing energy usage across them. To facilitate this sharing of data with the utility company, even if some of the homes go offline, requires storing data on available and reliable servers, for example, cloud. Applications for smart homes also share sensitive home data. Consider the example of Digital Neighborhood Watch. So an instance runs in a home and it monitors the footage from the security cameras. If it sees an activity, it records it. For example, if it sees a moving car, it records that it saw a car, its color was red, information like where the car entered from, where it exited from, etc. It requires support to tag data. Now to check if this activity is suspicious, for example, if the car simply cruised in the neighborhood without stopping at any home, it issues queries to neighboring homes, requesting to look at recent data tagged with car and red. But homeowners typically consider the footage from the security camera sensitive, so they do not want any unauthorized access to this data, and they do not want anyone tampering with this data. So this brings in the requirement of ensuring confidentiality and integrity of data. So to summarize, there is a need to store time series data, to be able to query data from specific time windows, to be able to tag data and filter data based on tags. There is a need to store data on the cloud to facilitate sharing and to store data reliably, and there is a need to ensure confidentiality and integrity of data. But none of the existing systems today fulfill these requirements. For example, consider time series data processing systems like OpenTSDB. These systems present an interface to do temporal range queries. They do store data in the cloud, but in these systems, the cloud and the database server can access the data and can modify the data, so these systems do not provide confidentiality or integrity of data. Secure systems over untrusted storage store data in the cloud, they provide confidentiality and integrity of data, but they expose the general key value interface, which is not suitable for time series data. So we need a new data management system, one that fulfills all the requirements. In the rest of this talk, I'm going to present the design of Bolt, a system that fulfills the requirements of applications for smart homes, and then I'm going to talk about the feasibility of Bolt for real-world applications. So applications for smart homes have these three requirements. How can we design a system to address them? Well, in order to satisfy the requirement of storing data in the cloud, two options come to mind. The first is to store the data in a database in the cloud. This automatically provides an interface to do temporal range queries. The data is in the cloud, but the cloud is untrusted. It can access the data and it can tamper with the data. So the data has to be encrypted before it leaves the home, has to be decrypted before it can be delivered to the application. Integrity metadata has to be generated before data leaves the home, and integrity checks have to be done before it can be delivered to the application. Also, if the cloud is asked to do computation on behalf of the application, then it can return incorrect results. So the computation also has to be moved to the endpoints. But now if you look at it carefully, we are not really using the database for much. We are simply using it to store and retrieve data. So why not use a key value store? This brings me to the second approach. So secure systems over untrusted storage store data in the cloud. They have logic running at the endpoints to do confidentiality and integrity of data, but they provide a general key value interface. So the first thing we need is some support for temporal range queries. Applications generate data records. So how can an application that generates data records use such a system? Well, an option is to map each data record to a key value pair, but that causes various inefficiencies. Each data record has to be encrypted and decrypted individually. Integrity metadata has to be generated for each data record. This not only causes computational overhead, but can cause significant storage overhead, especially for time series data, where often the data records are just a few bytes in size. Then each data record would have to be individually uploaded to the cloud or downloaded from it. And individual data records also do not compress well. So this loses the opportunity to compress time series data. So solution is to batch contiguous data records. And this works for applications for smart homes because they anyway look at multiple proximate data records within a query. So based on these design guidelines, Bolt presents a stream-based abstraction to its applications. Applications can append data records to a stream. Each record consists of a data value, a timestamp, and is associated with one or more tags. An application can share this stream with a reader application that can do lookups based on timestamps and tags. And Bolt stores data on the cloud, but it does not trust the cloud. So the cloud cannot access the data. A reader application can detect if the data has been tampered with by the cloud, and it can detect if the cloud is returning stale data. It also does not require the cloud to have a query engine to do lookups or to perform computation. I'm going to present the rest of the design of Bolt in three parts. I'm going to talk about writes, I'm going to talk about how reads work, and then I'm going to talk about key distribution. So a stream in Bolt consists of a data log and an index. The index is a map from tags to a list of offsets into the data log that are sorted by time. So when an application generates a new data record, it is appended to this data log, and a new entry is simply appended to this index. When this application now closes this stream is divided into chunks, where each chunk is then compressed and encrypted before being shipped to the cloud. But before this can be done, each of the chunk is also hashed, the index is hashed, and a signed hash of all of these hashes is also stored on the cloud alongside the data log and the index. So doing this chunking reduces the amount of data that has to be stored via compression and the amount of data that has to be transferred over the wire, and it also amortizes the cost of security. Now for reads, when an application wants to read data, Bolt, on behalf of the application, downloads the index. It verifies its integrity, decrypts it, performs lookups on this index, and the lookups are fast because it can use binary search as the offsets are sorted by time. It makes a list of chunks that it needs to download and downloads these chunks. Before it can deliver the data to the application, it needs to verify the integrity of these chunks and needs to decrypt and decompress them. But you may think that it downloads some extra data that is not going to be required by the application. But that is often not the case. Applications using Bolt typically have three types of query patterns. They either want to look at data from a fixed window, or they want to look at data in a sliding window or in a growing window pattern. Downloading in chunks reduces the number of remote calls for all of these types of queries. And downloading in chunks also prefetches some data that is used by subsequent queries, because they look at multiple adjacent time windows. So to enable applications to share stream, Bolt uses the model of decentralized access control. So if an owner of a stream wants to grant access to a reader application, it simply shares the key that it used for encrypting data, let's say key 1, by encrypting it with the public key of the reader application, and then it puts it on the key server. It can also revoke access for a reader application. And to do so, it simply generates a new key, let's say key 2, and then encrypts the fresh data that it generates after the revoke call with this new key. But there are a few challenges that need to be addressed here. If there are numerous revoke calls over time, the set of these keys that was used to encrypt data for a particular stream can grow big in number. And also, the key server itself is hosted on the cloud, so it cannot be trusted. So to do efficient key sharing, Bolt uses hash-based key regression. We're using the latest key, let's say key n, all the previous keys, key 1 to key n-1 can be derived. So only the latest key has to be stored and shared. Also, Bolt trusts the key server to maintain principal to public key mappings, and it trusts the key server to not roll back its state. If any of these two assumptions are violated, it is possible that there is unauthorized access to the data. A possible solution that Bolt can employ, but its current prototype does not, is to replicate the key server 2f+1 times to tolerate up to f corrupted key servers. So now that I have talked about the design of Bolt, I will talk about its feasibility for real-world applications. So we implemented Bolt and integrated it with Home OS. The code is publicly available. The current prototype of Bolt supports storing data on Windows Azure and Amazon S3. And we integrated Bolt with 5 applications, three of which was done by us, and 2 of which was done by other developers, which says that Bolt is fairly usable. So the first thing we wanted to understand about Bolt were its overheads. So we compared it to flat file storage, which is a system that does not provide support for temporal range queries and that does not do security. And we conducted an experiment. To do this comparison, we conducted an experiment where a micro benchmark client issued synthetic reads and writes to a Bolt stream. And while doing so, we analyzed the breakup of the query time and measured the storage overhead. So reads and writes in Bolt have 4 parts. For example, for writes, Bolt needs to do a lookup, it needs to serialize and write data to the disk, it needs to do compression, hashing, encryption, and it needs to upload data to the cloud. So we found that most of the query time was taken to either write data to the disk or to upload it to the cloud. And the story was same for reads. As a result, the time to do lookups and the time to do security related stuff was added only just 2% to the query time. So the overhead for the query time was low. Also, to support time series data, efficient time series temporal range queries, Bolt uses an index. And it stores some additional data per data value in this index, but this is constant for each data value. So if we increase the size of the data value, the percentage overhead is low. For example, if the size of each data value is 1 kilobyte, the amount of extra data that is stored in the index is 1% of the size of the data. After understanding the overheads in Bolt, we integrated it with various applications. The first application we integrated it with was energy data analytics. So recall that in energy data analytics, the utility company analyzes energy consumption across homes. Specifically, it plots the average hourly energy consumption as a function of the ambient temperature. And it does so for multiple homes, comparing energy usage across them. So we conducted an experiment to measure the time taken to do this analysis while varying the number of homes and while looking at energy data for the last 30 days. So first, I would like to note that it was straightforward to integrate energy data analytics, make it use Bolt. And the y-axis here shows the time taken to do the analysis. X-axis shows the number of homes. The blue bars are for Bolt. To give this performance number some context, we also integrated energy data analytics with OpenTSDB, which is a time series data processing system. But note that it is not an apples-to-apples comparison because OpenTSDB is written in Java, it stores data in HBase, and it does not provide any security. But despite that, Bolt performed better than OpenTSDB, despite providing more. And the reason and the benefit comes from prefetching of data. So to answer a particular query for a query for a particular temperature in OpenTSDB, the query is shipped to the database in the cloud, and the result is returned. But in Bolt, when it answers the query for a particular temperature, it also downloads some data that is used by subsequent queries that look at similar adjacent temperature values. So now this subsequent query can be answered by just looking at the local data cache instead of being shipped remotely. The second application we integrated Bolt was Digital Neighborhood Watch. So recall that in Digital Neighborhood Watch, an instance, in order to check suspicious activities, issues queries to neighboring homes requesting to look at recent data. So we conducted an experiment to measure this query time for 10 homes while looking at data from last 10 hours. And again, I would like to note that it was very easy to make Digital Neighborhood Watch use Bolt. The y-axis here shows the time taken to do this query. The x-axis varies the chunk size. We found that if the chunk size is 1 megabyte, Bolt performs better than OpenTSDB. But now, if we reduce the chunk size, reduce the size of this patch, Bolt needs to perform a lot more of remote storage calls in order to retrieve the same amount of data, so its performance decreases. This relates to the strawman 2, where we mapped each data record to a key value pair, thus increasing the number of remote calls and round trip times. We also measured the storage efficiency of Bolt and compared it to OpenTSDB. For 3 applications, PreHeat, Digital Neighborhood Watch, and Energy Data Analytics, Bolt is 3 to 5 times more space efficient than OpenTSDB. And the reason is twofold. First, all the security-related metadata in Bolt is stored per chunk instead of per data record, so it is efficient. And secondly, OpenTSDB itself is quite inefficient. It stores 1 hour of time series data in 1 row of HBase. And then for the next hour of data, it needs to replicate part of the index, part of the primary key. So this duplication increases the storage overhead in OpenTSDB. So to summarize, there is an emerging class of applications for smart homes. These applications have a unique set of requirements. They need support for time series data. They need to store data in the cloud. They need security, confidentiality, and integrity. These applications, none of the existing systems today fulfill these requirements. We designed Bolt that addresses all of these requirements simultaneously and efficiently by moving a lot of security stuff and computation to the endpoints and by leveraging batching and the nature of the queries. Bolt enables the development and deployment of applications for smart homes. And we found that it is faster and more space efficient than OpenTSDB, despite providing more, despite adding security. The code for Bolt is available, and we encourage you to use it and contribute to it. Thank you.
All right, thanks. We are opening for questions, and don't forget that we're also on the Twitter with Ask NSDI 2014. So let's open up to questions.
Rick Farrow. Yeah, so I like a lot of the design. Sounds very interesting. But I'm wondering if the code would actually work, say, if I wanted to do this with Linux. I already have a camera. I use MS SQL to store images and to do some of the same things you're doing for homes, homes security. But is this specific? Is the code specific to using Home OS?
No. So the code can run outside Home OS. So our first prototype actually ran outside Home OS. All of our experiments was done separately. But then we integrated it with Home OS because that adds value, right? Because applications,
more people can use it, yeah.
Applications already need to contact the sensors and devices in the home, so it integrates. So it provides storage and device interaction, right, at the same time. So that adds value. But it can run without Home OS. It does not depend on Home OS.
Okay. Well, thanks very much. Since nobody else is standing up, I was wondering who your test users are for the neighborhood watch kind of thing where you're sharing cameras. Are those Microsoft employees by any chance, or are they just ordinary people?
Oh, I mean, for the experiments here, the data is synthetic.
Oh.
For the experiments that I showed, the
Right.
data is synthetic. It's not generated like by actual homes as such.
Yeah, living in Arizona, I wonder how many of my neighbors will share their video camera in data with me. So, but thank you very much.
Hi, great talk. Marcin Kowalski. I would like to know if you had any ideas about dealing with what is fundamentally the kind of global clock problem that you're very reliant on time in time series data and time being accurate, and which means that you require that all your neighbors are using NTP and that all the clocks are in
Yeah,
sync.
so there is an assumption that the clocks are synchronized. So basically, when a reader application wants to read data, it needs to know what time the writer application wrote the data, right? So it all needs to be synchronized, but it doesn't have to be like perfectly synchronized. It can be loosely synchronized. And Bolt provides like a freshness guarantee. When a reader application reads data, it knows that it is not stale beyond a configurable time window. So the synchronization basically depends on that configurable time window. But yeah, we assume that the clocks are synchronized across homes, but loosely.
Okay, we have a couple minutes for additional questions. Maybe one question I'd like to ask while we're waiting for some others to come up to the microphone is, a lot of the applications you talked about sort of, and you mentioned fitting into Home OS, it seems like there's other communities of users that might be, for example, mobile, even a group of automobiles, for example, moving together, that may want services similar to the kinds you're offering in this environment. But they might have a lot less network connectivity to the cloud, but they may have a lot of network connectivity among each other. So have you thought a little bit about how you might modify this to support effectively mobile users?
So, I mean, if I reframe your question is, if there is not a good connectivity to the cloud, then can Bolt still work while leveraging the storage, perhaps using the storage on mobile devices? Yes, there is nothing in Bolt that prevents it from being deployed in a peer-to-peer architecture, so that can be done. But the reason we did not do that is because, I mean, it's hard to build peer-to-peer systems that are like highly reliable and available. So, but it is possible. Bolt is configurable to do that. So nothing prevents it, stops it from doing so.
So you're doing temporal analysis by using the data from a particular community. Let's say at 1 a.m. In this particular house, the temperature was set to whatever, and in the adjacent house, it was some other temperature. Let's consider there is a retarded office location that has employees coming in on different days, and they have, like, say, 10 employees on Monday, 20 employees coming in on Tuesday, 10 again on Wednesday, and 15 on Thursday. So based on that, can you change the parameters used to set or change the temperature in that particular office based on the number of users coming in on a particular day and repeat it every week?
I think that's like a very application-specific question. You can write like whatever application you need to do whatever intelligent analysis you want to do. But I don't think your question has anything to do with the storage capabilities. It's more to do with the algorithm of the application.
Yeah, I guess my question is more in terms of can the code be changed to handle such situations?
I think the type of algorithm that you're describing and the application that you're describing should be implementable on top of Bolt and Home OS.
Cool. Thanks.
Okay. All right, thanks again. Let's thanks the speaker again.